I didn't look at this in the last video, but I should have. I forgot to include this. But it was just going over a temperature measurement bridge circuit using a thermistor. And we build this on the breadboard and we test it in the waveform in the playlist link below the like button. The video will be near this. A thermistor is a resistor designed so the value of its resistance varies in a predictable manner as temperature is varied. It can be used to measure temperature using the Wheatstone bridge circuit shown in our figure 2. So this is our bridge circuit right here, and our resistor is on this bottom right corner right here. Note, our bridge circuit is typically drawn as shown to the left. We only redraw it on the right to illustrate that both sides of the circuit use voltage division to set the voltages on node A and B to a fraction of the applied voltage Vs, and this goes into our instrumentational amp that we're going to be using to amplify this. If the resistor on the bottom right has the same value as the other resistors in the bridge, so i.e. the delta R of it is equal to 0, then the voltage division is equal on both sides, so VA is equal to VB and VAB is equal to 0. However, if delta R is not 0, so the difference between our R is not 0, then our VAB depends on the value of delta R, according to this equation which we have here, and this allows us to find our delta R by measuring our VAB according to this equation. So if our thermistor is used as a resistor on the bottom right of our bridge, then the measuring VAB, we can easily determine that our delta R and with it the change in temperature. Since VAB can only be used in a few millivolts for small changes in temperature, it is common to use an instrumentational amplifier to amplify this small change in voltage to a larger value, and we just talked about this. An instrumentation amp is a special type of integrated circuit voltage amplifier built using several op-amps to achieve a very high input resistance and a very high CMRR, which is the common mode rejection ratio. In many applications such as this, it is desirable to amplify the difference between the two node voltages, but not amplify any voltage that is common to both nodes. The common mode voltage is often noise picked up from the surrounding environment, and we don't want any noise, or just the DC bias voltage on the two nodes, which you don't want. Neither of these are the different signal that we'd like to amplify, so ideally the gain for common mode voltages should be 0. While it's impossible to achieve this in our real integrated circuit amplifiers, instrumentation amps can achieve extremely low gains for common mode inputs, and an important figure to merit for these amplifiers is CMRR, which is defined as the ratio between the gain for different signals. And this is what we want. The gain for common mode signals, which is what we don't want. So instrumentation amplifiers can achieve values of CMRR of 100 dB or more. And that is just that whole paragraph right there. Our instrumentational amplifier that we're going to be using is the AD8226, and we use this equation to find the gain for it. And we also have more information here. Now we have more information to design a Wheatstone bridge with the thermistor and instrumentation amplifier. We're not going to be going over this. This is just going over how we would test this. So we could read that here. We need to use the thermistor and test whether we have something cold or hot with it. Now that that's done, we can look at the lab for it. And so for this lab, my partner and I, we did some descriptions, which should be shorter. We have images, we have calculations, we have spice simulations, and all that. We also have the breadboards for things that we've done, and we did good. This can be improved. We should have done it on like a OneNote and screenshotted it into here. Also, we should have done a little bit less on the descriptions, but also a little bit more accurate on them. And so we have these breadboards that look great as well with these waveforms. Those were the best part of the lab report. So next we can keep going down, and we see that we didn't fully do part 3 or a conclusion. We just ran out of time, but our part 1 is done completely. Not 100% as accurate as it would like to be. We would like to have shorter descriptions, more accurate ones, and also a better way to demonstrate our calculations. And then we should have also had more time to finish this. However, it is done, and that is it for this lab. There is a next video which we will be going over our axis tilt sensor.